Welcome to the Explainer. Okay, let's just dive right in today because we are breaking down something incredibly cool. We're looking at a highly ambitious, local first orchestration tool. And to be clear, this is not your standard web app. What we have here is a cutting edge architectural blueprint, completely generated by Google Antigravity 2.0 and Gemini 3.6. Its main objective? To act as a self contained local IDE and dynamic execution environment. Essentially, we're looking at the exact specs needed to run an entire agentic development environment straight from your machine. It uses browser technologies in ways that, frankly, feel like absolute magic.
To really wrap our heads around this complex system, we're going to treat it like a blueprint. We'll build the architecture layer by layer through 6 key topics. 1, the orchestration tool. 2, phase 1, host and auth. 3, phase 2, the isomorphic shell. 4, phase 3, microOS and monorepo. 5, phase 4, execution and LSP. And finally, 6, the system constraints that hold this whole thing together.
All right, section 1, the orchestration tool. Let's get a high-level overview of our foundation. As you can see, this architecture rests on 4 core pillars where responsibilities are really cleanly isolated. We've got our host layer, running as a .NET 10 console app. Then a shell, built as a reactive Next.js application. Our engine is powered by a StackBlitz web container, and the authentication is handled seamlessly by Azure Entra ID. It's just a really elegant mashup of heavy-duty backend logic with modern, hyper-fast front-end tooling. You know, it's serious when Gemini 3.6 itself describes the architecture this way. It explicitly calls it cutting edge, pushing the absolute boundaries of what's possible in browser-based computing. Because we aren't just running simple scripts here, we are dynamically pulling repositories, linking them up, and spinning up local servers right inside a simulated operating system, all within the browser.
Moving on to section 2, phase 1, host and auth. Let's look at how this builds from the absolute bottom and pour that foundation.
So the .NET 10 console app acts as the bootstrapper for the entire operation. Picture this. It wakes up, immediately parses your environment variables, things like your organization and tenant ID. Next, it triggers an interactive Microsoft Entra ID flow in your default browser. And while you're logging in, the console app is quietly spinning up a lightweight ASP.NET Core Kestrel server on your local host. That local server catches the OAuth loopback callback, caches your secure token, and then uses a process command to launch Chrome specifically in app mode. This strips away the standard browser UI, meaning our Next.js shell is going to look and feel exactly like a native desktop app. Now, here's a detail that is absolutely crucial, like make or break for the entire architecture. Kestrel must inject these strict cross-origin isolation headers into all of its responses. Why? Well, later on, our StackBlitz engine relies on a browser feature called shared array buffer to function. And due to modern browser security, shared array buffer dictates strict cross-origin isolation. If Kestrel doesn't inject those require corp and same origin headers, our web container engine, it's just going to fatal error right on launch. It's a tiny detail, but it has massive architectural implications. All right, section 3 brings us to phase 2, the isomorphic shell. The foundation is set, so let's construct the walls and windows. Running inside that Chrome app window is a Next.js UI container, configured as a static export, and the layout is incredibly focused. Up top, you have an Entra ID populated navbar holding your connection properties. On the left, a dynamic file tree component mapping out your workspace. But the real magic happens right in the main view, which is a split pane. On the left side, you've got the Monaco editor, yep, the exact same powerful editor that runs VS Code, and on the right, an iframe that directly outputs the dev server running inside our upcoming engine. Section 4, phase 3. MicroOS and monorepo. This is where we install the plumbing and the engine and, honestly, where things get truly wild. Before we go any further, it's vital we define our engine here, the MicroOS web container. Let's be real, this is not just a sandbox, it's a secure, browser-based operating system runtime. It lets us run Node applications natively inside the browser environment. No remote virtual machines, no Docker containers sitting on a distant server somewhere. The entire execution environment lives right there in the Chrome app window we just launched. And here is the brilliant orchestration sequence that fires off when the Next.js shell mounts. It boots the web container, authenticates using that Entra ID token we cached earlier, and fetches the root package.json from your targeted Azure artifact. But wait, it doesn't stop there. It actually scans those dependencies, hits the Azure DevOps Get Repositories API to find the source code, and uses isomorphic it, running entirely inside the browser, to dynamically clone those repos.
Finally, it rewrites the root package to create a workspace and links them all into a unified NPM monorepo. It literally builds an entire multi-repository workspace on the fly.
But there was a huge technical hurdle they had to overcome to make this work. See, traditional monorepos rely heavily on OS-level symlinks to connect local packages together. But web containers, for strict security and architectural reasons, struggle with standard OS symlinks. If you try it, the build just fails. So the brilliant workaround? Leveraging the Node 18 -- install links flag. Instead of symlinking, it natively resolves local binaries by copying the files directly. It perfectly bypasses the web container's system limits and allows the monorepo to function flawlessly. Next up, Section 5, Phase 4, Execution and LSP. We've got the code, we've got the editor, now let's flip the switch and turn the power on. Let's look at how the hot reload actually works. Because we have Monaco sitting right next to an iframe, we want instant feedback, right? So whenever a user types in the Monaco editor, it fires an on-change event. We debounce that for about 300 milliseconds, just so we don't overwhelm the system, and then write that new content directly to the web container's file system using fs.writefile. Because Next.js is running inside that web container, it natively detects the file system change and instantly triggers a hot module reload right in the adjacent iframe. Boom. Seamless, instant, local feedback. But here's a massive technical challenge. An IDE isn't really an IDE without autocomplete, error highlighting, an abstract syntax tree, or AST analysis. Normally, running a heavy TypeScript language server for this kind of code completion absolutely kills browser performance. It just freezes the main thread. So how do we fix this while keeping the app lightning fast? The fix is actually incredibly elegant. We separate the concerns using web workers in our web container. We initialize the Monaco language client, but instead of running the TypeScript server on the main browser thread, we spawn a TS server instance inside the web container itself. Then we create a duplex stream using the web container API and pipe the standard input and output streams directly to Monaco via a background web worker. The main UI thread remains completely unblocked, keeping everything lightning fast, while the heavy AST analysis happens in the background with incredible speed. Finally, Section 6, System Constraints. Let's wrap up this explainer by reviewing the strict boundaries of this whole setup. See, every single architectural choice here was a clever workaround. You must have strict file isolation between your Next.js shellcode and the Node execution scripts. The entire system pivots on the shared array buffer, which again is why that .NET host absolutely has to inject those coop/coep headers. The authentication relies on Chrome app mode sharing the OS session state, which makes that loopback redirect the cleanest possible approach. And all that dynamic Git resolving, it strictly assumes the structure of the Azure DevOps REST API v7.0. You have to respect these constraints or the whole house of cards just collapses. But hey, as the feasibility analysis from Gemini clearly points out, this isn't just theory. It is completely achievable and highly feasible. The key to unlocking this incredible local-first agentic environment is simply to strictly respect and correctly map these physical technology boundaries. Do that, and you have a remarkably powerful orchestration tool right at your fingertips. So we've seen exactly how to combine a .NET host, a Next.js shell, and a web container engine to build an entirely self-contained IDE in a browser. Armed with this architectural blueprint and these incredibly clever workarounds, what impossible local-first environment will you build next?